And we have here inner product. So let's put here G, which is this matrix ionized. And then the thing is that so this is inner product stuff, right? So if two disks, let's say A and B, they become vectors A. Let's put it like this. This means bold in our writing, right? So if they are tangent, AB is something else.
Also backwards.
With itself, A and A, which is the length of it, it's also. And then we have two possibilities, and I'm like changing sometimes. So, but recently you convinced me to make it +1, and therefore this will be -1. But I think I'll go back to the previous one eventually, but not like today. Okay. Last time also I suggested some.
Okay, that was. But then the video is ready. Carry on.
So is it not recorded?
It looks as though it is recorded.
Yeah, Yuri, put some pressure on your chalk. A little bit more pressure. Because then it doesn't show anything there.
The board's really dirty.
Oh, I see. Yeah, you're right. It's not because you got strong, right?
The lightning affected his vision.
Okay, so but this is something you already know, right? And the thing is, last time we looked at the full Apollonian packings. I'm putting those. What about now?
Yeah, it looks very good.
And we want to know what happens to this whole thing, the structure in the Minkowski space. So the thing is that it will be a crystal, kind of like a Platon space-time crystal, or let's say like Platonic solid, but higher dimension. Okay, because in 4-dimensional and maybe hyperbolic.
Is this these shapes something like Euler characteristic?
Or
do we have
unfortunately, there will be infinite number of things going to the same place. So in a sense, yes, but you have to make it a little funny, you know. But yes.
Okay, so you have a sequence of them. Can it possibly converge or something? Or eventually constant?
Do you know Schlafly numbers for Platonic solids? So they are better here. You also maybe I'll mention. But anyway, so I don't know how to draw it. Of course, I don't know how to draw it. But we can do one by one. For instance, if you have two circles, they become actually one edge. And you know what does what the edge means? Like in this Minkowski space, which is 4-dimensional, this means one circle is one vector. But we think about this point rather, point. And then we want to know what's the length of it, right? And you have to calculate it for this, for this, for this, for this, for this, for this, a lot of them. But look, this is the magic happening. This is, let's say, A, and this is B, okay? Or two circles, A and B. They become those two vectors, A and B. You take their difference and calculate their length. And at the beginning, I calculated using numbers. And then I later realized, look at this. All right, this is this squared minus the b. This is the norm of a vector. This is a standard thing, right?
Yeah.
You know that, right? So now, let's say using this here method, that a times a is +1, this is +1, and -2, and what is this? -1. Whatever they are, at the moment they tangent, however big, where this doesn't matter, this is really 4. So the length itself is 2. This means in the space-time, the distance between any two when they're tangent is 2. So 2, 2, 2, 2, 2, 2, 2, 2, right? All those guys. Now, of course, the next thing would be this triple. So same thing. And the distance is 2, 2, 2. I don't have to say it. And the picture will be an equilateral triangle. This quadruple here looks like very uneven, but here it will be 2, 2, 2, 2. I don't know. Something like that. And notice that this is composed from triples, which are mutually tangent. Means you have to glue together such things in four-dimensional space, and you get a crystalline structure representing Apollonian stuff. So isn't that weird? But this is in Minkowski space, so hyperbolic. You have to accept this. And then one thing is okay. Oh yeah, that's it. Just in case you have never seen it before. So notice that as you create Apollonian gaskets, so notice you start with 3 typically, right? And put the 4th one. So that's it. But then there is no other like 5th, which would be tangent to all of them, but it will be here, right? So if the first 3 were like that, where do you think is this one? Well, it's tangent to only 3 of them, but not to the 4th. It will be maybe something like this. What if you add this one? Oh, this will be then glued here, you see? What about this one? You know, and so on. So you build with gluing it together in that space, those tetrahedra. I have 2 already glued.
This is in hyperbolic space, though, yeah. So the
Yes.
picture is a little deceiving.
Well, yes, but so the thing is that every edge is space-like. You know, in space, this is space-time. Of course, I cannot draw all dimensions, right? So any edge is really space-like, but except that every edge is in a different space. You know, those spaces are under different angles. So that's like for physicists, it's a little strange here happening.
So the edges are really straight in some sense.
Oh yes, because I take the tips of those vectors and make this thing. You know, like for instance, in standard geometry, Euclidean geometry, how do you build Platonic solids? All of them are embedded in a sphere, right? Obviously. Sure. So, like for instance, here is one of the easiest to draw. So notice that the endpoints are on the sphere, although the vectors are like this, like this, like this. So if you want to know what's the distance here, take the difference of these 2 vectors calculated, and that's what we did. But we did it in a different metric. For sure. Okay. So here is something where one with the other one glued together. So if we continue, we'll beat this space-time thing, right? So, but the next generation of points, if you glue it together, you see here, there are gaps. So if I wanted to glue to this side, there is no space there. So there is no space, but in Minkowski space, because this is hyperbolic with this minus, yes, there is space, and you can glue it forever.
With no gaps.
No gaps. Okay. By the way, in ancient times, I think people, maybe Archimedes or somebody, claimed that space can be fully filled with, there were only 2 or something figures. One would be blocks, right? And another one would be tetrahedra, which is obviously wrong. You see? There's a discrepancy here. Okay, so that's something. You know, this is a crystal. I think it's a beautiful thing. And you can now ask different questions, like for instance, what's the symmetry? If you have something like this, you're asking about symmetry of that, right? Like the group of rotations and so on, preserving it. Same thing here. Another question here is, okay, I can look from this side and make a planar graph of those edges. If you want to understand just the graph theoretic structure of the edges, this is what you draw, right? And for each of Platonic solids, you can easily draw. Well, this solid, you can try the same thing. Draw all edges on a plane and see what you will get.
But each one has infinitely many neighbors or something.
Exactly. So this is what you do. Just connect this with this, with this, with this, just whenever they are tangent. And this is the famous Apollonian, they call it network, right? But they didn't think in terms of this, just okay. So Seth made a beautiful picture of this thing, right? So it was supposed to share with you guys, but still is.
Thank you, Jimmy.
Yeah, I brought it when I brought it in.
Yeah,
was
but you never
available on
said it.
Yeah, I need to get that to you. I haven't opened it up since then, but yeah, it's just.
So this is how you draw it. This is one of them. This is the fourth tangent.
Is
This
it like
is
a
new
weighted
tangent.
graph?
This is new tangent, you see, to this three. Just inside put every time a new one and so on, it become dense and unbelievable dense, right? Okay.
Well, we draw it with distance here. Graphs don't necessarily need distance. Do we
Yeah.
like bake in the weights or distances there, or
Here, no, you don't care about this. You can do this
otherwise, what is it isomorphic to or something?
as a
Just
graph.
As a graph?
Just to itself. It's just pretty unique structure. But this is not totally true because we have to start with this and then build this on every edge. That'll be better.
Mhm.
There is no make flatten it. People didn't notice it. This will be good only for just when you put things only here. See?
Wait, the graph is planar though, yes?
Yes. Well, the truth, for this it is planar. I think that for the whole thing, you need to go outside somehow.
So it would be planar, but maybe a cone.
Yeah.
Over.
So here, like for instance, this one, right? If you flatten everything on the original one, where is the original one like there, then you will get such a structure on each of
Yeah,
the four sides, and that will be it.
this would be good task, right?
Yeah.
Spot the K33 or K5 minor. Spot, there should only be one because I can remove one thing and get.
You think, but the thing is that there is such dense set of those faces. Maybe yes. Yeah, it's project.
Kind of one.
Yeah. But anyway, so this
Maybe
is,
not,
so
yeah.
I think we covered. It is, and look how simple this calculation actually, right? Everything is linearized so much that they can do. Now, another thing is, what are those angles between them? So I'll leave it to you, but it's the same thing, like the length of this, the cosine thing. So I leave it to you just to finish it. And again, do just these general calculations instead of particular numbers. Okay. So where do we go now from this to? One thing is go directly to the structure of the group, preserving it, which is really thing I think last semester before the last semester, those funny groups with matrices, remember? Maybe you weren't here yet. Like, SL2. Did you see this on the blackboard before? Written by me? Perhaps not. No. Okay, so this is one way to go. We'll take a little effort, but it's really great stuff. This is something everybody knows. This group is this guy extended by another element and makes something completely new and something to really, and research could be done. So I leave it maybe for another time because Leila couldn't come today. We have a guest, they can talk about. So I'll show you something which is cool instead. Okay, so slightly departure into something intriguing. Do you have any questions, by the way? So if not, I will show you something about Pythagorean triples. Is that okay?
I do think it is planar.
Okay.
Just
You want bet or?
Do you know for a fact it is not planar? If not, I think I see why.
No. Okay.
Take a point on the blackboard up above it. There are only countably many things that would be tangent here. You can make a.
Yes, but I think it would be very messy.
Very messy, but it's planar.
Yes, okay, then I agree. And give it this to start thinking about this planarity. No, you're right. I thought about this too, but then I tried to draw it.
You're not gonna
messy.
No.
Okay, so let me tell you something which I discovered some time ago already. This is actually published. And
Actually, if you wanted to draw it nicely, invert your thing. that is the outside disk will be in the center. It'll cone out like this, and
And
then
then
you'll
go
have,
outside.
then you'll have a beautiful
Yeah,
triangulation of the whole
yeah, I
plane.
agree.
Or not quite triangular. It's a triangulation.
Take another one. Okay, so Pythagorean triples, everybody knows what it is. The most famous is, so there are solutions, Z solutions to actually maybe N natural numbers to equation A squared plus B squared is equal to C squared. As you famously know, if you make a different number, like bigger than 2, things don't go well. I mean, you cannot find it, right? But there's other which it kind of works. What could, instead of 2, we can put it, we still sort of working. That you could
That's
get
1 or 0.
yeah, and -1.
Oh,
You know, you can get 1/3 plus 1/6 is 1/some, yeah, so you can figure out. But anyway, cool. So there are specials. So you have 3, 4, 5, 12, 8, 13. That's everything I remember. But in ancient times, when people were building altars and so on, they were looking for higher levels because they thought this is like truly godly thing to do. And can you classify them? So there is a famous classification by Euclid that just there's one parametrization that always you get one. Well, there's a theorem. Maybe I'm not going to cover. I want to show you first the cool thing. Now, some time ago, when in Fortis, yeah, 64, Barney came up with the following idea. Start with 3, 4, 5, make it maybe a vector, and you will get all possible other Pythagorean triples the following way. You have 3 matrices. I'll put them. Oh, there we go. Okay. 3 matrices. U, which is 1, 2, 2, 2, 1, 2, and 2, 2. Can you guess? Of course, you have seen it. 3 for some reason. Okay. This is U. Let's see, L would be the same thing. Would be 1, 2, 2, 2, 1, 2, and 2, 2, 3. And yet another is 1, 2, 2, 2, 1, 2, and 2, 2, 3. Okay, 3 different matrices. Of course, they're not different, but they will now be. Okay. So the thing is that act with this matrix on this vector. Should we take one of them at least? Like for instance, yeah, let's take this one and act on this vector, okay? 3, 4, 5. So 3 plus 8,
Oh, 11.
11 plus 10,
That's easy. 22, of course.
21. Okay, what about this one? 6 and 4, 10,
Plus
10,
10.
20.
Sounds reasonable.
Okay, what about this one? I'm quickly calculating this. If I have this paper with me. So you're getting a new one. Okay.
Well, we should check, right?
Yes.
Whether it actually works, but
Okay, so 20 is like 400 and 400. Yeah, 29 squared. So, well, after the lightning, do you get numbers easier?
No, actually, after lightning, I don't know what number means.
Oh,
okay.
ignore everything I said. Okay.
They aren't real.
So the thing is that you see, I'm not going to draw it, but you're getting a new one, a new one, a new one, and again, new one, new one, new one.
It will always be new.
Always new. And guess what? Every existent triple shows up only once. Only once.
Once and only one.
Once and only once. And for instance, this one, you know, there is another one which is very similar. It won't show up. Once this shows up, this does not. Okay, so it's like truly unique Pythagorean triple sets. Okay, so this is Barney, and this became famous, and now in Wikipedia, actually, this is displayed, and this is maybe small variation on the order. Okay, so it's not well-known fact, but pretty cool. On the other side, I made it like closer to what Wikipedia have, but I've also like shuffled them so better fit to what they have. Did you know something?
No, I didn't.
That's something new.
Silly-ish question for you. Namely, are these matrices invertible? If so, what happens if you start with 3, 4, 5 and actually try to
Go
go
at it.
backwards and then
Yeah, you'll get the negative. I think.
okay.
Right. So this is, we have to think about this U, L, and R. You're taking all possible words in it. So you're writing computer graph, I think you also use it words, right? Like U, L, L, R, U is a word in this alphabet.
What a horrible word.
Don't say it. So this word would correspond to one of them. Means go here, 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 here. So you're taking all possible products of these things, and such a thing is called semigroup. Instead of group, semigroup, because you don't take inverses. But you can take inverses to go, and you get some loops, by the way. You know.
Oh, yeah.
So let's keep it all simple on the thing. And then the thing is, you can draw those triangles, each of them, but you have no idea like what is geometry of that stuff. And good news, when you look carefully in Apollonian window, you will see it, and you will also reconstruct those matrices, and that's what I thought I would show you today. Okay? So here's our, it opens from one side up here. I don't know if you see the old picture, but there's more numbers.
The nicer print, smaller, easier to manage.
Yeah. Well, the true beauty of this is this.
That you can beat
Listen,
us up with
listen.
it.
Ah, now stop. Amazing. And the frequencies are actually corresponding to one of them. Okay, so guess what? Where we can find them? Look here, 3, 4, 6. But subtract 1 will be 5.
Okay.
Look here, 5, 12, 13. One of those which I remember.
What about the 1, 0?
6,
Oh, yeah, that was-
10 is also Pythagorean triple, right? But it's not anymore. This is like 4, 3, 10. It is this one doubled. Oh, yeah, change the order.
Sure.
But what about this one? What about this 21? Can I see it somewhere?
Maybe you can.
No, yeah, you're right. But anyway, you'll notice that anybody who is tangent to this external line will correspond to some Pythagorean triple, each of them. So if this one and this one, then this one in between, and in between, in between. So you have infinitely many of them. Okay.
I'll let you keep
Go ahead.
going. No, I think you're about to answer it. So
Maybe not.
these induce a map on this. How does it act? Can one draw the
Exactly.
arrows you're about?
Exactly. So they like jumping, and right now we don't know. Okay, right now we don't know, and also we don't want to take them like all of them. Only the ones which are really the so-called primitive Pythagorean triples are the ones which show up only once, and they are not multiples of something before. Okay. So we need to make a discovery, and I'll just tell you right away what is the discovery. So I take it away because we have it. And that's why sheer trying everything. I did the following thing. First of all, let me remind you one thing. It will be easier maybe to work in something like this. Remember x dot, y dot, and beta and gamma, right?
Wait, I have a question. I'm sorry.
Go ahead.
You only end up with the primitive ones doing this procedure.
Yeah.
Okay.
Yeah, that's beauty, just exactly the right set. So maybe shocking, right? So remember, we write it this way. This is the position exactly, all right? And beta is, remember this? Yeah, I don't have to remind you. We write it this way. So, but we can rewrite it in a slightly different coordinate system. Okay, X, Y, and here Z and T dot dot, which is same thing as X dot Y dot. Z will be beta minus gamma, and here beta plus gamma over 2 over 2. This is, this is the two different coordinate systems in Minkowski space. So we'll do this one, and this is standard, let's say, remember ST. We can do it here, but this will be quicker. All right, now, okay. Yeah, let me first, instead of, because, yeah, we will be running out of time, I'll tell you right away what happens. This is the main circle, okay? Now, notice that there are symmetries. This is one symmetry, and this is another symmetry. If you do it, then the Apollonian window will stay the same, right? This is only half of the Apollonian window. But there's also another one, A. There is another one, namely this circle. If you make inversion of this through the circle, roughly it will go inside, but not really. Because look, there is the right angle. So this will go to itself. And everything here, like this one, will go here. I mean, it really goes onto itself. It is preserved. Believable or not?
Because of this line, they're perpendicular.
Yes.
So,
Yeah, so all this Apollonian gasket will be still the same, but the circles will go to different places. So let's call it C. This inversion through this will go C. And now notice the following thing. What we care is about, remember, the ones which are tangent to it. So if I do A, where is A? There's one of this one, I forgot.
did you name them? No, you named them.
Okay, you do A. So every point goes here, here, here. Every circle here goes here, here, and so on. So all these guys tangent to this go to tangent to this. So A. But then when I apply C, so all these guys will go to part of it.
Sure.
Okay, so we have one thing. Another thing, go B first. So all these guys go there. But under the inversion, like this, will go somewhere here. So also goes back to some subset. So C and B will do the job, getting out and in.
You mean do the job?
Of,
What's the job?
shuttling those points here, and the job is not well defined, right? But the thing is that this circle, for instance, will go outside and then under inversion somewhere here.
Okay.
With this will go right here, and under inversion maybe somewhere here. It will be again tangent. Or we can go this way, take a circle, go completely across, and under inversion will get smaller, will go somewhere there. So C after AB, same thing as C, BA, because AB is
BA, big.
right, same thing. Okay, so I have two such things. And guess what? In Minkowski space, these are almost exactly these matrices. So
What do you mean almost exactly?
because let's see.
Okay.
Yeah, so why it works. So suppose we have A, B, C, this is a Pythagorean triple, or A squared plus B squared, C squared, okay? Embedded into that thing. So how would you do it? This embedment, we can move like this. This is a circle A, B. Now the curvature will be C plus 1, right? If you want this triple to be represented by this, will be 3, 4, and 5 plus 1. And the gamma, remember how you have gamma is what? A squared plus B squared minus 1 over curvature C plus 1. Is it right? But this is C squared minus 1 over C plus 1. But C squared minus 1 is C plus 1 times C minus blah, 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 blah. Cancellation will be C minus 1. You know that this thing is C plus 1 times C minus 1. So you cancel this, this is what you get. So our gamma is C minus 1. Okay? So every triple shows up here as one of those circles which are tangent to the. Now, we want the thing in the standard, I mean, we not necessarily, but we will change it into the standard basis. Means A, B. Now, for Z, will be beta minus gamma. This minus this over 2.
So 1.
1.
Oh,
And then this plus this over 2.
C.
C. Okay. So every triple goes to a vector in space-time looking like that. Now we can apply one of them. We'll do just one and see because the others behave similar way. I suggest this one. Okay. You change the sign, right? So this is changing the sign of X. This is changing sign of Y, and then we have to do that stuff. So, okay, so let's say, okay, AB. It will be minus A minus B1C, right? Under this inversion. But then let's do capital C. This is not small c, this is capital C, right? So maybe like this. So it'll be A, B, C. Do you remember inversion? No, it worked. Oops. One more metal. So do you remember inversion? Inversion, we found out is really reflection in the Minkowski space.
But yeah, there you go.
Thank you. Man, after the thunder,
Yeah, the brother gives you idea.
gee.
Electrifying.
So remember, you have to take this vector. Oh, let me remind you. This is the vector we have to reflect along this vector. So you subtract twice the projection, right? So it will be still the original one minus twice. Should we call it now V twice V? Oh, let me write it. Twice minus A minus B1C, comma, here our vectors for which we do that thing, and here the thing. This is our N and N. This is N. You remember this? So what is our N? Our N is this big circle, and this big circle has 0, 0, 1, minus 1. Right, this curvature, oh, minus 1 actually, plus 1. It doesn't matter really. But if you want to write in a standard basis, so 0, 0, this plus this over 2,
0.
0, so it will be 4 times 0. And this minus 2, this will be minus 1. Oh, no, sorry. We are inverting with respect to this.
That circle,
This circle,
which has points
1, 1, right? So its thing is 1, 1, radius is 1, and this plus this is squared is 2 minus 1, 1. I think this is the circle.
Oh, that's nice.
But we want to make it into standard. So it will be X, Y, here Z will be this minus this, and so this plus this over 2, 1. So this is the one.
Okay.
If we want to do it in the standard notation. So 1, 1, 0, 1, 1, 1, 0, 1. So this is, we have an exercise in the thing we developed last time. Okay, so what is it? Minus A minus B 1. This was 0, I hope.
Yeah, C?
C, I hope. Minus, now look at this. This is minus A minus B
Plus 0
plus 0
minus C.
minus C because
We do.
this is time.
I learned some even in the standard because we changed bases.
Because
we're in the standard basis.
yes. So this is exactly the reason. Right. Let's see whether it corresponds to anything I have written here. Yeah. So you got it right. So it's twice A plus B plus C. And then our normal vector is this one. 1,
I thought we
1,
said minus.
0, 1. What is minus?
I thought we said A plus B minus C.
Minus, yes, but this would be like, look, minus A minus B, and with the minus would be plus.
Okay, someone should have a different sign though. A, B, and C on that.
So A and B are positive.
Oh, no, now I see. Now I understand.
Because you asked me to change it to positive.
Oh, I did?
Not you, but you.
Okay, I'm happy again. I forgot something very important.
Okay, so you have sum of two vectors. What is this sum of two vectors? Well, this means that this guy shows up here, here, and here, right? As a coefficient. Minus A plus 2A plus 2B plus 2C. So minus A, so we just A plus 2B plus 2C. Agree? The first entry. Here, minus B, taken away from this, so it will be only one B, but 2A, 2AC. 2A plus B plus 2C. Remember, this is not a matrix, it's a column. What about the third one? 1 plus 0. 1. And then C would be,
you get 3 C's and 2 of every.
yes, 2A plus 2B plus 3C. Now look, this was the map going from triples to this, Okay? So how do we undo it? First, make sure this is 1, and then you see here A, B, and C. So this means this is certain matrix of, this is going to A plus 2B plus 2C. We just ignore that one here. 2A plus B plus 2C, and here 2A plus 2B plus 3C. And this can be written as a big matrix acting on A, B, C. Namely, because this will be 1, 2, 2, 1, 2, 2. To get this, 2, 1, 2, 2, 1, 2. And here, 2, 2, 3, 2, 2, 3. Ta-da! Right on time. So isn't that amazing? Thanks. So we're getting those 3 matrices. Still, who knows why it works so beautifully, and that I was just playing with it until I got it. So this is like really finding something by taking every stone and looking for this underneath. It's not that I had a theory how to get there. It was accidental discovery. So therefore, we have an interpretation of Barney matrices, which are partially known, to something which is not very much known. They publish it, maybe they did, but nobody reads papers nowadays. So we got Apollonian window contains the secret somehow of those Barney matrices. We have geometric interpretation of those matrices.
That's amazing,
isn't it? So there are many jewels in this, in that stuff. It's not the only thing.
Yeah,
so we already know that this in space-time becomes something, right?
Yeah. You have to retire in order to appreciate.
No, it's enough that you got struck by thunder, by the lightning, right? And what else they wanted to tell you about this? Okay, a very simple homework, maybe. Yeah, you can of course do the other ones, right? Like what if you only do only A or only B? There will be minuses somewhere. And you can guess that this is why you're getting those minuses in the columns. They survive, and that's it. Okay, and the other thing would be that show that anything tangent to the big one here inside, wherever it is, it will have in this description always one. It's very simple exercise. With things you know, you can easily get it. But I think if you're looking for something you can calculate on your own, right, you can try it. Okay,